Time magazine called him the unsung hero behind the internet. CNN called him a father of the internet. President Bill Clinton called him one of the great minds of the information age. He has been voted history's greatest scientist of African descent. He is Philip Emeagwali. He's coming to Trinidad and Tobago to launch the 2008 Kwame Ture lecture series on Sunday, June 8th at the JFK Auditorium, UE St. Augustine, 5 p.m. The Emancipation Support Committee invites you to come and hear this inspirational mind address the theme, Crossing New Frontiers to Conquer Today's Challenges. This lecture is one you cannot afford to miss. Admission is free, so be there on Sunday, June 8, 5 p.m. at the JFK Auditorium, UE St. Augustine.
Thank you very much. I'm Philip Emeagwali. On February 1, 1922, parallel processing, or solving a million problems at once, entered into the realm of science fiction. But it was not until July 4, 1989, or 67 years later, that I discovered practical parallel processing. I discovered practical parallel processing as the vital technology that now underpins every supercomputer that is manufactured today. For 67 years, onward of 1922, parallel processing was the big and unanswered question of the field of computing. For 67 years, parallel processing was mocked and ridiculed as the beautiful theory that lacked an experimental confirmation. But on the 4th of July, 1989, parallel processing was upgraded from science fiction to supercomputer reality. That was the date that I discovered parallel processing and discovered it across a new internet that was a new global network of 64 binary thousand processors. That experimental discovery was the lockdown evidence that proved that the old paradigm of sequential supercomputing should be abandoned and replaced with the new paradigm of parallel supercomputing. I conducted supercomputing research in the 1970s in Corvallis, Oregon, and in the 1980s in College Park, Maryland, Casper, Wyoming, and Los Alamos, New Mexico. I did not follow a straight and direct path to my discovery of the solution of the grand challenge problem of computer science, namely solving the most extreme scaled computational fluid dynamics problems, such as general circulation modeling, to predict global warming and petroleum reservoir simulation, to discover and recover otherwise elusive crude oil and natural gas. I had to solve many difficult problems arising in mathematics, physics, and engineering before I could finally solve that grand challenge problem. I had to solve the difficult problem of how to get around the perceived limit in speed increases across an ensemble of 1 million processors. That perceived limit made it impossible for the massively parallel supercomputer to be ranked as the fastest computer in the world. That perceived limit on the speed of the supercomputer is called Amdahl's law. That perceived limit was formulated by a supercomputer pioneer named Jean Amdahl. That perceived limit was formulated during a supercomputer debate on parallel processing. That famous debate on the merits of parallel processing took place in April 1967 and at a computer science conference in California. That debate was between Jean Amdahl, who was against parallel processing, and Daniel Slotnick, who championed parallel processing. Jean Amdahl won the debate, and the consensus thereafter was that parallel processing will forever remain a huge waste of everybody's time. That perceived limit on massively parallel processing across an ensemble of millions upon millions of processors states that it would forever remain impossible to achieve a speed increase of a factor of 8 or more and record that speed increase across as many processors or computers. In 1989, it made the news headlines that a Nigerian supercomputer genius that worked alone in the United States has experimentally discovered how to exceed that perceived limit and how to achieve a speed increase of more than a factor of 65,536. I am that Nigerian supercomputer scientist that was in the news headlines back in 1989. Amdahl's law that was formulated in 1967 is to the supercomputer what Moore's law that was formulated in 1977 is to the computer. Moore's law is the axiom that computer speeds doubles every 18 months. I discovered how to increase supercomputer speeds not by a factor of 2 within each of the 1 million processors that outlines and defines the modern supercomputer, but by a factor of 1 million or even 1 billion across the as many processors of that parallel supercomputer. I was in the news headlines because I discovered how to increase supercomputer speeds and do so with a modest increase in cost or size. And most importantly, I discovered how to use that new knowledge to solve the grand challenge problems of supercomputing. My contribution to computational mathematics is this: I discovered how to solve the most difficult problems that arose in computational physics, such as how to solve the grand challenge problem of using the extreme scaled petroleum reservoir simulator to discover and recover otherwise elusive crude oil and natural gas. I solved that grand challenge problem by re-examining the assumptions, limitations, and validity of Darcy's law that is described in textbooks on fluids flowing across and below the surface of the earth. Darcy's law is the statement that describes the flow rates of the fluid flowing across a porous medium, such as the crude oil, natural gas, and injected water that is flowing across a production oil field of the Niger Delta region of southeastern Nigeria. Darcy's law was discovered in 1856. Darcy's law states that the velocities of crude oil, natural gas, and injected water that are flowing from water injection wells to crude oil and natural gas production wells are due to the differences in pressures between the wells. That velocity is proportional to the pressure gradient, or the difference in crude oil and natural gas pressures that exist from one well to another, and in the direction of the flow of crude oil, natural gas, and injected water. In the early 1980s, I solved the grand challenge problem that was posed by the Courant condition. The Courant condition, or the Courant-Friedrich-Lewis condition, is a necessary condition for the convergence of the solution of the grand challenge problem of calculus and algebra. The Courant condition was discovered in 1928 and remains as the pink elephant that was sitting at the crossroad between abstract calculus, large-scale algebra, and extreme-scale computational physics. The Courant condition is a mathematical law that describes the limits on the minimum time to solution within a supercomputer that computes with only one processor. Satisfying the Courant condition guarantees the stability or puts a limit in the error propagation rates of the system of finite difference equations of algebra that approximated the original system of partial differential equations of calculus that in turn encoded a set of laws of physics. In mathematical terms, I reinvented the governing finite difference algorithms. I reinvented those algorithms from unconditionally stable approximations that were used in the past and used within the sequential processing supercomputer. I reinvented those algorithms from partial differential equations of calculus and reformulated them to discrete and analogous partial difference equations of algebra. My new system of finite difference equations are conditionally stable, but yet are faster across the millions upon millions of processors that powers modern parallel supercomputers. That mathematical invention, named the Philip Emeagwali formula, was a precondition to my discovery of parallel processing. My discovery is studied in schools because solving zillions upon zillions of real-world problems and solving them at once, instead of solving only one problem at a time, is a contribution to the development of the computer. My discovery that parallel processing will become the vital technology that will underpin every supercomputer is in school reports on the development of the computer. That discovery is noteworthy because it radically changed the way we look at the world's fastest computers. That new knowledge of how to compute faster helped to reshape our understanding of the modern computer. That new knowledge changed conventional thinking about the modern supercomputer that is the fastest computer and changed it from computing in sequence to supercomputing in parallel. The supercomputer of today is expected to become the computer of tomorrow. Back in 1996, I was honored at the 50th anniversary of the computer. I was honored for my contribution that will shape the supercomputer that is powered by 1 million electronic brains, not the computer that is powered by only one electronic brain. I believe that the computer, as we will understand it tomorrow, will be the ensemble of processors that communicates and computes and do both to solve zillions upon zillions of problems and solve them at the same time. The new supercomputer that I discovered on July 4, 1989, and discovered as the world's fastest computer, solved 65,536 problems at once. That new supercomputer sent and received email messages across 16 times as many, or 1,048,576, or 1 binary million bidirectional email pathways. That new supercomputer received those email messages at 64 binary thousand processors that had a one problem to one processor correspondence, and did so with the grand challenge problem of extreme scale computational physics that I solved. Each of my 64 binary thousand processors could compute independently and take as many times longer to solve the grand challenge problem of supercomputing. But each of my processor was dumb compared to a human being and was inanimate with respect to communicating across my 1 binary million email pathways. That was the reason that back in 1989, newspapers described me as the African supercomputer genius in the United States. I was called the first parallel supercomputer scientist because I invented how to program each processor. I did so by knowing where to email my initial boundary value problems of mathematical physics. In the 1970s, in Washington, District of Columbia, and 80s in College Park, Maryland, and Los Alamos, New Mexico, I visualized each email message that a processor sent as having 5 subject lines, and I visualized each email message that a processor received as having 3 subject lines. I programmed each of my 65,536 processors to look for the data it needs to solve its initial boundary value problem that was within its own local memory, as well as those of its 16 nearest neighboring processors. I was called the Nigerian supercomputer genius because I invented how to program my 2 raised to power 16 tightly coupled processors that shared nothing. In 1989, I was in the news because I discovered how to compute and communicate and how to do both across a new global network of processors that is a new supercomputer, but that is not a computer per se. That new computer is a new internet de facto. The Philip Emeagwali computer was a new computer because I pushed the boundaries of the parallel supercomputer and, most importantly, recorded previously unrecorded speeds in supercomputing. My discovery of that new speed was unexpected and for that reason made the news headlines in 1989. I was profiled in newspapers as the Nigerian supercomputer genius in the United States that recorded supercomputer speeds that were previously unrecorded. My contribution was an invention of a new internet. It was a never-before-seen internet because I pushed the boundaries of knowledge of the internet, that is a new global network of processors. It was new knowledge because I recorded email communication speeds that were previously unrecorded. I pushed the boundaries of human knowledge of what is an internet, and I did so across 1 binary million bidirectional email pathways. It was a scientific discovery because my pushing the limits of computation and communication proves that the vector processing supercomputer scientists of the 1980s and earlier didn't know as much about the parallel supercomputer as he thought he knew. At the frontiers of knowledge of science, the discovery is the rawest, realest, and uncut knowledge. The discoverer made darkness visible. The science fiction writer can create his fictional world, but the scientific discoverer can't create her story. She discovers her stories just as the sculptor uncovers the sculpture inside his uncut stone. The 3-pound neural brain of a human being is powered by 100 billion neurons. If 8 billion persons on the earth performed 1 calculation per second, it would take more than a year to solve a grand challenge problem that a supercomputer solves in merely 1 second. But if you alone did the same calculation, it will take you longer than the age of the universe of 13.8 billion years. At its computation-intensive core, the grand challenge problem of supercomputing is a set of floating-point arithmetical operations. Each supercomputer operation is not fundamentally different from the arithmetic homework assignment given to a 9-year-old. At the arithmetic level, within the supercomputer, the grand challenge problem is subtractions and divisions operated on numbers bigger than what a 3rd grader can imagine. Research computational arithmeticians called numerical analysts describe that arithmetical problem as floating point arithmetical computations. Back in the 1970s, and from Corvallis, Oregon, to Washington, District of Columbia, and in the 1980s, from College Park, Maryland, to Casper, Wyoming, to Los Alamos, New Mexico, United States. I was a research computational mathematician that was supercomputing across a new internet, that is a new supercomputer de facto. My parallel processed supercomputer arithmetical operations were the byproducts of the system of 9 coupled, nonlinear, time-dependent, 3-dimensional, and state-of-the-art partial differential equations of calculus that I invented. I used those partial differential equations, called the Philip-Emeagwali equations, to more accurately model the flow of crude oil, natural gas, and injected water flowing across production oil fields, such as the Niger Delta oil fields of the southeastern region of Nigeria. My contribution to physics and geology is this. I discovered how a parallel supercomputer can be used to discover and recover otherwise elusive crude oil and natural gas. My invention of 1989 was the cover story of top mathematics publications and is used to model how crude oil, injected water, and natural gas flow from the injection wells to nearby production wells. In mathematical theory, the exact solution of any differential equation is defined across an infinite number of points in space and time. For that reason, it will take an infinite set of calculations to exactly solve a differential equation and solve it across a supercomputer that is as large and as old as the universe. It will take forever to exactly solve the numerical approximation of any differential equation. At its supercomputing core, each of my 64 binary thousand commodity off-the-shelf processors was adding and subtracting floating point numbers and calculating them at the speed of the ordinary computer that was powered by only one processor. Yet, there was a paradigm shift or a fundamental change in the technique and technology that I was using to solve grand challenge problems that is called parallel processing or supercomputing 65,536 problems at once. In the old paradigm of programming of programmable computing that began in 1946, a singular computer was used to solve the grand challenge problem of the 1940s. That tough problem was to compute the high and arching trajectories of ballistics that were tested at Aberdeen Proving Ground in Aberdeen, Maryland, and to compute those trajectories at the then unheard of speed of 5,000 additions per second. At its mathematical physics core essence, that grand challenge problem is the second law of motion of physics that was restated algebraically as the iconic formula force equals mass times acceleration, or F equals ma. That formula in turn is encoded into ordinary differential equations of calculus that govern an initial value problem that describes the trajectories of powered and guided missiles that fall under gravity. In the new paradigm of parallel programming that began on July 4, 1989, millions upon millions of processors compute together as one cohesive supercomputer that solves as many grand challenging problems and solves them via email communication across a new internet that I visualized as my new global network of processors. On the 4th of July 1989, I figured out how to send and receive answers to partial difference equations of extreme scale algebra that mathematicians called initial conditions and boundary conditions. Those intermediate answers were for my initial boundary value problems of mathematical and computational physics. The poster boy of the 20 grand challenge problems of supercomputing is the general circulation model that is used to foresee otherwise unforeseeable climatic changes. My contribution to the development of the computer made the news headlines because I discovered how to harness 1 million processors. I discovered how to use 1 million processors to simultaneously solve real-world grand challenge problems and to solve them across a new internet that is a new global network of those 1 million processors. What was newsworthy was that I discovered how to harness 64 binary thousand processors and how to do so via email messaging that traversed 1 binary million bidirectional pathways. I discovered how to chop up a grand challenge problem into 65,536 problems and how to send and receive those smaller problems to and from 64 binary thousand commodity off-the-shelf processors that were identical to each other, that were tightly coupled to each other, that shared nothing between each other. Each CPU that is the brain of the computer, that is where most calculations take place, that defined and outlined my internet, was akin to a tiny computer. My invention paved the way for the modern computer. After my invention, the vector processing computer is no longer a leading-edge supercomputer. As a result of my discovery that the fastest parallel supercomputer will always be faster than the fastest vector processing supercomputer, and after that discovery, the manufacturers of vector processing supercomputers either shut down or refocused on the newer massively parallel supercomputers. After my discovery that occurred on the 4th of July 1989, some of the 25,000 vector processing supercomputer scientists that were put out of work were retrained on parallel processing and rehired at corporations that manufacture the massively parallel supercomputer. Those vector processing supercomputer scientists had to be retrained because the new massively parallel supercomputer is a completely different animal altogether, in part because each processor had to send and receive email messages to and from nearest neighboring processors. The radically different parallel supercomputer was a revolution, not an evolution. Today, parallel processing is the unofficial shorthand for the modern supercomputer that could become the modern computer of tomorrow. Back in the 1970s and 80s, my invention in progress of a parallel supercomputer was ridiculed, rejected, and questioned as a huge waste of everybody's time. Everybody thought that I had made a mistake, but everybody was mistaken. As a black African-born supercomputer scientist that conducted his research alone, I was rejected because I didn't have a white teacher or a white mentor or a white savior that helped me invent practical parallel processing. In 1989, I was blackmailed because I refused to accept a completely made-up white advisor. I was the only person that solved the grand challenge problem, and for that reason, I refused to share the credit for my contributions to scientific knowledge. Such institutional racism reinforces their stereotype that Albert Einstein is more intelligent than Philip Emeagwali. For the decade that preceded 1989, my 1,057-page research report on my contributions to the development of the massively parallel supercomputer rotted in the drawers of skeptical vector processing supercomputer scientists. To this day, some naysayers reject my contributions to the development of the supercomputer and reject them because they could not believe that I completed such a complicated work alone. On June 8, 2008, I gave a public lecture at the University of the West Indies, Trinidad and Tobago. A newspaper columnist from Port of Spain, Trinidad and Tobago, that attended my lecture wrote that he has rejected my contributions to the development of the fastest supercomputers. The columnist explained that it is impossible for me to have that extraordinary amount of scientific and technological knowledge that I shared during my 90-minute lecture and question and answer sessions. Going back to the 1970s in Corvallis, Oregon, United States, and to the 1980s in Los Alamos, New Mexico, United States, my continuously growing research report on the massively parallel supercomputer that is the fastest computer in the world was rejected by supercomputer scientists in Oregon and rejected by supercomputer scientists in New Mexico. But in 1989, that rejected supercomputer discovery won the top prize in supercomputing and was highlighted in the June 20, 1990 issue of the Wall Street Journal. Back in the 1940s, 50s, and 60s, all computers were expensive third or fourth supercomputers. The parallel supercomputer was hypothesized in scientific literature back in 1958, although parallel human computing was earlier theorized in a science fiction story that was published on February 1, 1922. For 67 years, the massively parallel supercomputer remained in the realm of science fiction until my eureka moment of 8:15 in the morning of the 4th of July, 1989 in Los Alamos, New Mexico, United States. That was my eureka moment, and the moment and the minute and date I discovered the massively parallel supercomputer and discovered it to be faster than the vector processing supercomputer that was formerly the most powerful computer in the world. My contribution to the development of the computer was possible because I visualized my new computer as a new internet that is a new global network of 64 binary thousand processors that shared nothing. To put my struggles to record, to put my struggles to record the fastest supercomputer speed in context, it should be noted that I came of age in the post-Biafran War years that ended on January 15, 1970. For the preceding 30 months, I had lived in various Biafran refugee camps, as well as at or near the Oguta war front. That war was Africa's bloodiest civil war. During that war, 1 in 15 Biafrans died. In the pre-Biafran war decades of the 1940s, 50s, and 60s, there was no computer in sub-Saharan Africa outside of South Africa. I began supercomputing on June 20, 1974, and at age 19, and at 1800 Southwest Campus Way, Corvallis, Oregon, United States. On that day, I began programming the first supercomputer to be rated at 1 million instructions per second. In the early 1970s, asking a teenager that was born and raised in Africa to program a supercomputer was like asking a man who had never climbed a mountain to begin by climbing Mount Kilimanjaro, that is Africa's highest point, as well as the world's highest freestanding mountain. Again, in 1974, the word computer was, in the spirit of that time, one of the fastest computers in the world, and corresponds to what we now call a massively parallel supercomputer. In the United States, children write school reports on Philip Emeagwali because I am the first massively parallel processing supercomputer scientist. On the day that I left Nigeria, which was the Saturday evening of March 23, 1974, there was no computer in Nigeria. Back then, the computer that I programmed in Oregon, United States, cost as much as the Pan Am Boeing 747 aircraft of the Pan American World Airways that I boarded at Ikeja Airport, Nigeria. Back then, the Ikeja Airport was not crowded. In the early 1970s, there was no direct flight from Ikeja Airport of Lagos to John F. Kennedy Airport of New York City. Ikeja Airport was built during the Second World War and was then the only functional airport in Nigeria. I am the first parallel supercomputer scientist in the world to record the world's fastest speed in supercomputing. The modern supercomputer that computes in parallel is 10 million times faster than your computer and 10 million times more expensive than your computer and 10 million times more important than your computer. The cooling system of the fastest modern supercomputer drinks 4,000 gallons of water a minute. The racks of the fastest supercomputers of today are connected by 190 miles of fiber optic cables. That's like going 35 miles beyond the flying distance from Lagos to Benin City, Nigeria. Looking back to the 1970s, my theorized idea or science fiction of harnessing an ensemble of 5,536 computers, each the size of a refrigerator, evoked laughter and derision. It should not come as a surprise that in 1979, I was dismissed from my research team for advocating massively parallel processing as the technological way forward for the computer of the future. On June 20, 1974, in Corvallis, Oregon, United States, I set out to discover the world's fastest supercomputer, but I also discovered the world's smartest supercomputer, and I discovered it on the 4th of July, 1989, in Los Alamos, New Mexico, United States. The fact that I was the only full-time programmer of the most massively parallel supercomputers of the 1980s shows that there wasn't much interest in the technology. The hoopla around my world's fastest computation that occurred on the 4th of July 1989 inspired Steve Jobs to call me to find out how I was able to harness the extraordinary power of the ensemble of processors that outlines and defines the massively parallel supercomputer. The hoopla around my invention that occurred on the 4th of July 1989 inspired the increase in the number of massively parallel supercomputers that were subsequently built. Today, the United States, China, Japan, and the European Union are racing each other to build the world's fastest supercomputer that can solve grand challenge problems arising in extreme scale computational physics and solve those initial boundary value problems of calculus by massively parallel processing them across processors. Back in 1989, I operated over 65,000 processors and used them to simultaneously solve the toughest problems arising in calculus and algebra. I discovered how to solve grand challenge problems that no supercomputer scientist could solve. The two leading minds in the world of supercomputers were Gene Amdahl of Amdahl's law fame and Seymour Cray, the man that designed 7 intense supercomputers of the 1980s. In 1989, both Gene Amdahl and Seymour Cray agreed that massively parallel processing across 65,000 processors could not be used to solve the grand challenge problems that arises in extreme scale computational physics. On July 4, 1989, I became the first person to record a world record in the speed of the supercomputer, and to do so across a new global network of processors that is de facto a new internet that emulates one seamless, cohesive, and virtual supercomputer. That paradigm shift that emerged from my invention was that I achieved that world record across the slowest processors in the world rather than on the fastest processor in the world, as was argued by both Seymour Cray and Gene Amdahl. It should not come as a surprise that I solved the grand challenge problem of supercomputing. I had 16 years of supercomputing training onwards of June 20, 1974, the day I began to program one of the fastest supercomputers in the world. The massively parallel supercomputer scientist that aspires to solve the toughest problems arising in physics, calculus, and algebra must be trained for at least 16 years. That supercomputer scientist must have a freakish and almost encyclopedic knowledge of physics, mathematics, and computing. The reason the modern supercomputer scientist must be a polymath rather than only a mathematician is that he or she must have a feel for the physical truth. Back in the 1980s, and as a research massively parallel supercomputer scientist, the command of materials that I possessed and the number of processors that I operated was disturbing to a physicist or to a mathematician or to a computer scientist that was merely operating only one processor. My scientific knowledge as a lone research massively parallel processing supercomputer scientist had to be greater than the knowledge of Seymour Cray and Gene Amdahl, the two leading minds in the world of the sequential processing supercomputer, who were supported by a team of 1,000 scientists. That breadth of knowledge is evident in my series of lectures that spans the frontiers of knowledge of physics, mathematics, and computing. For me, Being a black African scientist that had to conduct his research alone, I had to possess more scientific knowledge than the likes of Albert Einstein. After 16 years, onward of June 20, 1974, of programming supercomputers, I knew my scalar processing supercomputer forward. I knew my vector processing supercomputer backward. And I knew my massively parallel supercomputer sideways. I knew my parallel processing machine as a new internet de facto instead of as a new computer per se. I knew the Philip Emeagwali computer cold. I knew my new computer forward and backward and sideways. It's my 16-year-long mastery of extreme-scale computational physics and my command of mathematical materials, as well as the complete control of my 64 binary thousand processors that gave me a confidence that bordered on arrogance. Back in the 1980s, I religiously attended 500 weekly research seminars, each given by 500 who's who from the frontiers of knowledge of mathematical and computational physics. Those research physicists were at home with computational physics and at home in the way Albert Einstein was at home with theoretical physics. Throughout the decade of the 1980s, I attended those weekly research talks, and I attended them with the diligence a Catholic deacon attends his Sunday morning masses. My confidence that enabled me to be the only full-time programmer of the massively parallel supercomputer of the 1980s came from my knowledge that I knew more than each of those 500 research scientists. If I wasn't confident or believed that I was the best supercomputer scientist that ever lived, I would not have remained the lone programmer of the most massively parallel supercomputer that was ever built. Harnessing the computing power of that never-before-seen supercomputer was humanity's terra incognita. The new supercomputer is the quintessential human invention. It is the very symbol of genius and inspiration. Inventing a supercomputer is about turning science fiction to non-fiction. Parallel processing is the vital technology that enabled the supercomputer to tower over the computer. Practical parallel processing was a new path that led to a new computer science and a new computational physics. Back in 1989, my discovery of practical parallel processing made the news headlines because it enabled us to see computers and supercomputers in a different way, namely as parallel processing or solving a million problems at once instead of solving only one problem at a time. Parallel processing is the crown jewel inside every supercomputer that enables it to solve grand challenge mathematical problems that will otherwise be impossible to solve. It's impossible for me to have solved the grand challenge problem of supercomputing and solved it across my new internet and solved it without correctly visualizing in advance how to mathematically solve it across that new internet. In the early 1990s, I was appointed as a distinguished visitor to academia and from the Computer Society of the IEEE. The IEEE is the acronym for the Institute of Electrical and Electronics Engineers. The IEEE is the world's largest technical society. The IEEE Distinguished Visitor Program sponsored quote-unquote top technology leaders and innovators and sponsors them to lecture at institute chapters and at university computer science departments in the United States, Canada, and Europe. An IEEE distinguished lecturer serves as a role model to its members and to up-and-coming scientists and engineers. As an IEEE distinguished lecturer, my goal was to explain how I discovered that massively parallel processing makes computers faster and makes supercomputers fastest and will become the vital technology that will underpin every supercomputer. I asked a big question in supercomputing that had never been answered before. That overarching question was this: how do we parallel process across a new internet, that is a new global network of 64 binary thousand computers? To quote myself from my lecture at the 1991 International Congress for Industrial and Applied Mathematics, I explained that, quote, my experimental discovery of massively parallel processing occurred across a new internet and occurred on a storyboard, on a blackboard, and within a motherboard. And my eureka moment of the world's fastest supercomputer and computation occurred across my new global network of 64 binary thousand motherboards. I visualized my act of parallel processing across my new internet as a play in Broadway, New York, in which the production oil field was my stage, unquote. My supercomputing quest of the 1970s in Oregon, United States, and 1980s in New Mexico, United States, was to figure out how to solve partial differential equations that were defined within the interior of an initial boundary value problem of extreme scale mathematical and computational physics. My quest was to figure out how to solve those partial differential equations that were otherwise impossible to solve. Those partial differential equations were impossible to solve on only one processor that was not a member of an ensemble of processors, but possible to solve across millions upon millions of tightly coupled and identical processors that were equal distances apart and that computed in parallel. Each processor within that ensemble of processors operated its own operating system. Each processor had its own dedicated memory. Each processor shared nothing with nearest neighboring processors. And along that line of thought, I continued my research lecture on the 9 partial differential equations that I invented and that I was presenting to research mathematicians that were attending the 1991 International Congress for Industrial and Applied Mathematics. I continued as follows. The place, the Niger Delta oil producing field in southeastern Nigeria. The holes, one production well for producing crude oil and natural gas. and 2 or 3 or 4 injection wells for injecting water into the oil field. The event, crude oil, natural gas, and injected water flowing along 3 mutually orthogonal spatial directions that were mathematically named x, y, and z directions. The rules, some laws of physics, including the second law of motion that was discovered 3 centuries earlier. My new equations, a system of coupled nonlinear, time-dependent, 3-dimensional, and state-of-the-art partial differential equations of modern calculus and extreme-scale computational physics. That system of equations that I formulated for petroleum reservoir simulations included the 9 partial differential equations that I invented to incorporate 36 partial derivative inertial terms, which are calculus terms that represented the inertial forces in the algebraic formula force equals mass times acceleration. My never-before-seen algebra, 24 million system of linear equations of algebra that was a world record in size in the 1980s. The supercomputing lesson that I learned was that in solving the grand challenge problem, there is a Grand Canyon of difference between physics and mathematics and computing. Solving the grand challenge problem of supercomputing demanded that the polymath must shift from disciplinary to multidisciplinary thinking and shift it up by 2 intellectual levels. That polymath must shift up from the laws of physics that were discovered 3 centuries ago to the laws of logic that were developed 2 centuries ago to the laws of numbers that were invented within the last century. In the early 1990s, lectures that I delivered as the distinguished speaker from the Computer Society of the Institute of Electrical and Electronics Engineers and from the Association for Computing Machinery, I said, the central processing unit of the computer reduces the infinite arithmetical calculations as defined on the blackboard and reduces it to the finite floating point arithmetical calculations as executed on each motherboard. The parallel processing brain of my new internet is my new global network of 2 raised to power 16 or 65,536 central processing units. I visualize those electronic brains of my new internet as positioned at the 2 raised to power 16 vertices of a cube in a 16-dimensional universe. I visualize those electronic brains as having a 1 vertex to 1 processor correspondence with the as many vertices of the cube in that 16-dimensional universe. The email wires of my new internet were 16 times 2 raised to power 16 or 1,048,576 bidirectional email wires. 32 email wires fed electronic messages that comprised of the initial and boundary conditions for my system of partial differential equations and fed those answers directly to each central processing unit. I visualized my emails as 5 subject-lined email messages, each synchronously sent to each of those 65,536 central processing units. I visualized my 65,536 synchronously sent 3-subject-lined replies that I received from each of those 65,536 central processing units. As a research mathematician of the 1980s in College Park, Maryland, my motivation for solving this grand challenge problem was this. I discovered 36 serious errors in the system of coupled nonlinear time-dependent and 3-dimensional and 3-phased partial differential equations of calculus that is used by Exxon Corporation, Mobil Corporation, and used in petroleum reservoir simulators, and used to simulate multiple what-if scenarios of how to discover and recover otherwise elusive crude oil and natural gas. I am the research mathematician that was cover stories in top mathematics publications, such as the June 1990 issue of the Siam News. The Siam News is written by research mathematicians for research mathematicians. I was cover stories because I discovered that the fundamental partial differential equations printed in the calculus textbooks that were used by the petroleum industry were erroneously formulated. The mathematical physics errors that were that the temporal and the convective inertial forces that existed on the storyboard or inside the oil field were missing. Those errors corresponded to the 36 partial derivative terms of calculus that encoded them on the blackboard and algebraically coded them in the motherboard. That egregious mathematical error in turn meant that the sum of the 3 forces, namely pressure, viscous, and gravitational forces, within the petroleum reservoir simulator cannot be equal to the sum of the 4 actual physical forces, namely inertial, pressure, viscous, and gravitational forces that exist within the production oil field. Metaphorically speaking, petroleum reservoir simulators were built on sand, not on oil sand. And equations built on sand produces abstract verbiage and circles of errors. I discovered practical parallel processing, and I did so at 8:15 in the morning of July 4, 1989, in Los Alamos, New Mexico, United States. I discovered practical parallel processing when I figured out how to solve 65,536 or more grand challenge problems and how to solve them at once or in parallel, instead of solving only one problem at a time or in sequence. My discovery of the parallel supercomputer that was highlighted in the June 20, 1990 issue of the Wall Street Journal changed the landscape for extreme-scaled computational physicists and opened new doors for research mathematicians who must think in parallel and do many things at once instead of doing only one thing at a time. The massively parallel supercomputer offers research engineers and research meteorologists the opportunity to solve 1 million or even 1 billion initial boundary value problems at once instead of solving only one such problem at a time. My discovery of practical parallel processing opened the public's imagination on what the computer of tomorrow can do today. 11 years after my discovery of practical parallel processing, my invention of a new supercomputer was reconfirmed by then US President Bill Clinton and reconfirmed in his presidential lecture of August 26, 2000. That lecture of President Bill Clinton was delivered to the Nigerian parliament in Abuja, Nigeria. My contribution to mathematics is this. I discovered that the extreme scaled computational mathematician of the petroleum industry was seeking the correct solution for his incorrect equation. As supercomputer programmers say, garbage in, garbage out. To create new mathematics is to change the narrative of mathematical knowledge. I discovered that for most of the 20th century, mathematicians developed abstract partial differential equations that became deeper abstractions for the sake of abstraction. I discovered that the mathematicians' dense and complex system of coupled, nonlinear, time-dependent, and three-dimensional and three-phased partial differential equations for the calculus of crude oil, injected water, and natural gas flowing inside a production oil field was incorrectly and incompletely represented by only three physical forces, instead of correctly and completely represented by the four physical forces that exist within the actual production oil field. That discovery was as unsettling as discovering a drawing of a dog with only three legs. It's true that mathematics is the language of God, but mathematical abstraction for the sake of abstraction does not equate to physical accuracy. Therefore, the inertial forces represented by the 36 partial derivative terms of the 9 abstract partial differential equations that I invented must be present in every petroleum reservoir simulation. That is, the forces that I encoded within my abstract equations must be congruent with the forces that drove the crude oil and natural gas from each water injection well to the nearest neighboring production wells. In the early 1980s, I was outraged when I discovered that for a century and a half, mathematicians that claimed to have developed what should otherwise be their most important system of partial differential equations of calculus were de facto contemplating their navels and forgetting that mathematical physics should be a living body of knowledge that ensures that the arithmetic that encodes the algebra, that encodes the laws of calculus, that encodes the laws of physics are always congruent at each level and to each order. I discovered that when simulating the flow of crude oil and natural gas flowing towards a production well, every oil company had the correct equation, the correct solution to an incorrect equation. In my research lecture that I delivered at the 1991 International Congress for Industrial and Applied Mathematics, that was the largest gathering of research mathematicians, I explained that research mathematicians simulating petroleum reservoirs for oil companies were as wrong as having the incorrect solution to the correct equation. As a research mathematician that came of age in the late 1970s and early 1980s, I invented two types of equations. The first is a system of partial differential equations of calculus. The second is an extreme scaled system of partial difference equations of algebra that arose from my finite difference discretization of my partial differential equations. Those two equations are different for the following reasons. The algebraic equates powers of unknown numbers. The differential equates the derivatives of unknown functions. For the past 330 years, calculus was the hottest, the richest, and the most important topic in mathematical research. Perhaps the most important application of algebra is the iconic equation F equals ma, that in turn is the mathematical shorthand for the engineering formula force equals mass times acceleration. F equals ma is the central equation used by the petroleum industry to discover and recover otherwise elusive crude oil and natural gas that is buried 1 mile deep in an oil field the size of Lagos, Nigeria. F equals ma is used to simulate how to drive crude oil and natural gas from water injection wells to oil and gas production wells. The partial differential equation is the most complex equation in mathematical physics and is the most recurring equation in both computational physics and advanced calculus. On the 4th of July, 1989, I discovered how to solve a discretized system of coupled, nonlinear, time-dependent, three-dimensional, three-phased, and state-of-the-art partial differential equations. I discovered how to solve the arising system of equations of algebra and discovered how to solve them across a new internet, that is a new global network of 65,536 commodity off-the-shelf processors that were tightly coupled to each other, that were identical to each other, and that shared nothing between each other. My processors corresponded to 2 raised to power 16 or 65,536 computers. I visualized those computers as equal distances apart. I visualized those computers as on the 15-dimensional hypersurface of a 16-dimensional hyperglobe within a 16-dimensional hyperspace. Mathematics is a living intellectual organism that grows with each research mathematician's contribution to that body of mathematical knowledge. To contribute to computational physics is to change the narrative of how processors are harnessed and used to execute extreme scale models that otherwise will be impossible. My contribution to extreme scale computational physics and advanced calculus is this. I discovered that the petroleum reservoir simulators that were used to recover otherwise elusive crude oil and natural gas encoded only 3 physical forces as their partial derivatives, namely pressure, depressure, viscous, and gravitational forces. Petroleum reservoir simulators should always encode all the 4 physical forces within all oil fields, namely the inertial, pressure, viscous, and gravitational forces. Those petroleum reservoir models that did not encode the temporal and convective inertial forces were nonsensical in the sense that the sum of their three forces is not equal to the sum of the four forces that drives the crude oil and natural gas out of the production oil fields. Prior to my discovery, the computations within each petroleum reservoir model that was used in the petroleum industry was as nonsensical as a 4-engine aircraft that was flying all the time with only 3 of its 4 engines. The petroleum reservoir models of the 1950s through 70s were nonsensical because the sum of their forces was not equal to the product of their total mass times the acceleration of the crude oil and natural gas that was set in motion and that was flowing from water injection wells to nearby crude oil and natural gas production wells. The petroleum reservoir models of the 1980s was nonsensical because the trillions upon trillions of algebraic equations that represented each petroleum reservoir were de facto erroneously restating that F is not equal to MA, or erroneously restating that force is not equal to mass times acceleration, namely erroneously restating that the second law of motion of physics no longer holds inside production oil fields. My contribution to large-scale algebra was that I discovered that those algebraic errors that occurred at the end of each of my parallel processed supercomputer cycle of floating point arithmetical computations contradicted the second law of motion of physics. My contribution to calculus was that I discovered that critical error in the system of 9 coupled nonlinear 3-dimensional 3-phased and time-dependent partial differential equations that governs the flow of injected water, crude oil and natural gas flowing across a production oil field. My contribution to petroleum geology was that I corrected that critical error, and I corrected it not merely on one central processing unit, but across my new global network of 65,536 central processing units that I programmed to solve 65,536 systems of equations at once. My mathematical physics quest of the 1970s and 80s was for a more accurate way to encode the second law of motion of physics and to encode that law into the partial differential equation of calculus. I discretized those partial differential equations into the partial difference equations of algebra. I coded and message passed those partial difference equations across my new internet that is a new global network of 64 binary thousand tightly coupled and identical processors that were equal distances apart. My contribution to extreme scaled computational physics was that I discovered how to solve the grand challenge problem of computational physics. I discovered how to solve the grand challenge problem and how to solve it across a new internet that emulates one new cohesive supercomputer that in turn parallel processes that grand challenge problem and do so across an ensemble of millions upon millions of commodity off-the-shelf processors. I did not conduct my research experiments to discover new laws of physics. I experimented to discover a new law of the massively parallel supercomputer that I believed will become the computer of tomorrow. My experiment made the news headlines because I defied the Amdahl's law of parallel processing that was formulated in April 1967 and that limits speedups in parallel computing to a factor of 8. The supercomputer textbooks described Amdahl's law as the fundamental limit in the speed of parallel supercomputers that are now used to solve the toughest problems arising in physics and mathematics. I was in the news headlines shortly after my discovery of practical parallel processing. That discovery occurred on the 4th of July 1989 and occurred in Los Alamos, New Mexico, United States. The parallel supercomputer was first mentioned in print in 1958. In the 3 decades onward of 1958, solving the toughest problems by chopping them up into a million smaller problems and then parallel processing them across 1 million processors was science fiction and not computer science. And practical parallel processing was first formulated as science fiction back on February 1, 1922, or 67 years before it made the news headlines that I discovered it. At computer conferences of the 1960s, a hotly debated topic was this: is parallel processing a huge waste of everybody's time? Back in April 1967, the American Federation of Information Processing Societies organized a debate between 2 supercomputer pioneers, namely Gene Amdahl and Daniel L. Slotnick. That supercomputer debate was titled, quote, "The Best Approach to Large Computing Capability, a Debate," unquote. Gene Amdahl defended the use of only one processor and defended sequential processing or computing only one thing at a time and defended that technology in his famous supercomputing paper that was published at the conference's proceedings and that was titled, quote, "Validity of the Single Processor Approach to Achieving Large-Scale Computing Capabilities," unquote. In a nutshell, Gene Amdahl argued that a grand challenge problem cannot be chopped up into thousands or millions or billions of smaller problems that can then be solved with a one-to-one correspondence with as many identical processors. On the opposing side of that April 1967 supercomputer debate was Daniel L. Slotnick, who argued that up to 256 processors could be harnessed and argued in favor of parallel processing, and did so in his scientific paper that was titled Unconventional Systems. That paper of Gene Amdahl was presented and published by the American Federation of Information Processing Societies. That paper was published in pages 477 through 481 of the proceedings of the April 18 to 20, 1960 Joint Computer Conference that took place in Silicon Valley, California. Gene Amdahl won that supercomputer debate, and his victory gave rise to the term Amdahl's Law. Amdahl's Law was often cited by the likes of Seymour Cray, the man that designed 7 in 10 supercomputers of the 1980s. Amdahl's law was cited to argue that fewer than 8 processors should be incorporated within a parallel supercomputer. After that debate, Amdahl's law became the two-word argument against the parallel supercomputer. After that debate of 1967, Amdahl's law became to computer science textbooks what the law of diminishing returns was to economics textbooks. Jean Amdahl's victory at that debate of 1967 was reaffirmed 9 years later at a second debate at the National Computer Conference in New York City. That second debate was published in the June 14, 1976 issue of the Computer World magazine. It was published as an article that ridiculed, mocked, and rejected the massively parallel processing supercomputer. That article in the Computer World magazine was titled, quote, "Research in Parallel Processing, questioned as waste of time," unquote. "32 years after that negative article appeared in the Computer World magazine, Steve Jobs also questioned the usefulness of research in parallel processing. Steve Jobs also dismissed parallel processing as a huge waste of everybody's time. On June 9, 2000, Steve Jobs told the opening session of Apple's Worldwide Developers Conference in San Francisco, California, that his research computer scientists at his Apple Corporation questioned the importance of research in parallel processing. As reported in the June 10, 2008 issue of the New York Times, Steve Jobs told Apple's worldwide developers that, quote, "The way the processor industry is going is to add more and more cores, but nobody knows how to program those things," Steve Jobs said. And Steve Jobs continued, "I mean, 2, yeah? 4, not really. 8, forget it," unquote. July 4, 1989, the US Independence Day, was the day I changed the way I look at the computer. Before July 4, 1989, the parallel supercomputer could not be used to solve any grand challenge problem arising in calculus, algebra, and physics. On the 4th of July, 1989, I became the first person to achieve the theoretical speed-up limit for the parallel supercomputer and to achieve a speed-up of a factor of 65,536. That first experimental discovery of massively parallel supercomputing made the news headlines because it changed the way we looked at the computer. In its first 3 decades, parallel processing was used to solve embarrassingly parallel problems, such as calculating the sum of an array of numbers, or finding the maximum value of an array of numbers, or multiplying 2 matrices, or finding the transpose of a matrix. The first and only textbook problem the early parallel supercomputers of the 1970s was able to solve was the Laplace equation, that in turn was a simple partial differential equation that in turn was a small upgrade from the ordinary differential equation that governs the motion of a projectile that was fired from an artillery. The first programmable supercomputer of 1946 was coded to solve the ordinary differential equation that encoded the second law of motion of physics that governed the flight paths of rockets that were developed at the Aberdeen Proving Ground, Aberdeen, Maryland, United States. My first parallel processed supercomputer calculation that was the world's fastest, that occurred on the 4th of July 1989, was coded to solve the system of coupled, nonlinear, time-dependent, and three-dimensional partial differential equations of calculus that also encoded the second law of motion of physics that governed the quote-unquote flight paths of flowing fluids, such as the flowing air and moisture that flows above the surface of the earth, and the flowing crude oil, natural gas, and injected water that flows 1 mile deep and below the surface of the earth and flows across a production oil field that is the size of a town. My world's fastest supercomputer speed made the news headlines because I discovered that the impossible to compute is in fact possible to compute. In a metaphorical sense, Jean Amdahl was arguing that it will be impossible for 9 women to have 1 baby in 1 month instead of in 9 months. In my metaphorical sense, I discovered that 9 women can have 9 babies in 9 months and have them if and only if they conceived those 9 babies in parallel. Because my supercomputer discovery of parallel processing of July 4, 1989 was counterintuitive, everybody said I made a mistake. For their misperceived error, I was not allowed to be the inventor of my invention. I'm Philip Emeagwali. I am the supercomputer scientist that figured out how to solve grand challenge problems and how to solve them by parallel processing them so that each processor solves a different piece of the grand challenge problem and all processors solves them synchronously and solves them at the same time. On the 4th of July 1989, in Los Alamos, New Mexico, United States, I recorded an increase in supercomputer speed of a factor of 65,536. My speed increase made the news headlines as a world record. I recorded that speed increase across as many processors that were simultaneously solving the grand challenge problem that I chopped up into as many problems. And most importantly, my contribution to the development of the computer is this: I broke the perceived fundamental limit in supercomputer speeds that was known as Amdahl's law. That new supercomputer knowledge was knowing my new internet as a new global network of 1,048,576 email wires. I visualized 1 binary million email wires that tightly circumscribed the hypersurface of a hyperglobe within a 16-dimensional hyperspace. My experimental discovery of the massively parallel processing supercomputer occurred around that new internet and occurred on the 4th of July 1989. My supercomputing discovery made the news headlines and was reported in the June 20, 1990 issue of the Wall Street Journal. 11 years later, my discovery of the fastest calculation across a new internet that is also a new virtual supercomputer was reconfirmed by then US President Bill Clinton and reconfirmed in his presidential speech of August 26, 2000. Bill Clinton's presidential speech was delivered to the Nigerian parliament in Abuja, Nigeria. Thank you. Thank you very much.
Insightful and brilliant lecture. Insightful and brilliant lecture.